go through questions. We're just going to be going through questions for week 5 and 6 and for everything for week 7. Sorry for this. This is a tutorial on week 5 and 6, okay? And we're going to be going through the questions through every single question of it. And this is a practice of how we're going to be doing it in the test. So remember the first thing we do in the test. So let's do it the same way we're going to do in the test, the same way we're going to be doing here. What is the first thing we do? Write down our formula. So it's just going to be week 5 and 6, and we're going to be using them for each one of these problems. So let me see. Okay, it's fine. What are we going to do? Let's put the formulas. We start with the formulas for I. We know that I is equal to, from never, but we don't write E now. It's NQ, then VD, then A. Okay, for area. This is drift velocity. So, and we know that N is just going to be Avogadro's number. And then we multiply the electrons and divide it by the molar mass. Okay. And then we know that drift velocity is a velocity. So it's distance over time. It's like speed is distance over time. So drift velocity is going to be the length divided by the time taken to move. The length of your conductor divided by the time it takes for the electron to move across that length. Then area is area of a circle, which is the face of the wire, which is pi r squared, or it is pi multiplying d over 2 all squared. Okay. Now from here we have the first one for I, then we can put the other 2 because I should have 3. I is also going to be equal to delta Q over delta T. Then we also have the other one, which is going to say I is now going to be equal to, for current, again this is current, we'll be now saying that I is going to be equal to, remember this is now for orbiting electrons, it's VE over 2 pi r, but the E should be in modular signs, divided by 2 pi r, like this. This is going to give us our current. So we have the formulas for current. And then now we're going to put the formulas for resistance. We have 2, which is going to be R is rho L over A. Then we can have the other one, which says R is going to be equal to R naught square bracket 1 plus alpha. Then we say open T minus T naught, close, like that. Okay, here is my R. Then from there, what am I going to do? Put the one for delta V, which is going to be IR. And then I'm going to have, what else am I going to have now? I'm going to have, that is one for delta V. Then I need one for charge, which is going to be total charge delta Q is equal to the number of electrons, which is the number of particles, times the charge on 1. Now we know that if we make delta N the number of things, the formula, then if E goes to the other side, sometimes we may have to put a modulus on it to make sure that we get a positive number of particles. Okay, we have to get a positive. Now what else are we going to be looking for? What else have we left? What other important? P. Oh, we can put for P. P is going to be, we need the 5, which is going to be delta V times I. Then the other one is going to be power, is going to be delta V squared. Okay, delta V all squared divided by R. Then we can have again another one which says P is equal to I squared R, which is the power dissipated or power lost. Right? Then we are going to have 1, 2, 3. Then the fourth one is going to be power is energy over time. Okay? And we use this a lot when we're calculating cost of electricity, because we need to find energy, we make energy the subject, blah, blah, blah. And then we have the final one, which is the total power we have of the bulbs is going to be the power rating of one bulb times the number of bulbs. Okay, so this is going to be it. Then what else am I going to have? So I have the 5 formulas for power. Then I now need to put the J. J is equal to sigma E, okay? And E is the electric field. Remember that J is the current density. And what is sigma? Sigma is going to be the conductivity. Conductivity. Because this rho here for resistance is rho. This is going to be resistivity. And it helps me to find resistance. Now from here, I can also now say J is also equal to the current density, which is current over the area. And sometimes I may need to put this on my current modulus. That is if your current is negative, okay? If your current is negative. Then finally, you're going to have a relationship between conductivity and resistivity. And we know that conductivity is 1 over resistivity, which means the reverse is true again for resistivity. It is 1 over conductivity. With this, I can say I'll be done. Now I'll just put the ones for week 7. Let me put the ones for week 7. What are they? We say the one for EMF, E is going to be IR plus IR, right? Then we're going to have the one for maximum charge in a capacitor. It is going to be CE. That's the formula for maximum charge. The maximum charge that can be stored in a capacitor. Then from there we had for power generated, which was IE, which we also said it was I squared R plus I squared small r. This is for power generated. So here we have it. Power generated. Power generated. Now we have another one for power delivered. We would say power delivered. We said it was delta V times I. This is going to be for power delivered to your devices. Okay, power delivered, because there is going to be some power loss inside the source. Okay, due to the internal resistance of the source. Then if I have put this P is delta V I, then remember I should now then just put the one which says delta V battery plus the delta V resistor plus the delta V capacitor is equal to 0. This, remember, is for that one circuit which has a resistor and a capacitor. Okay, then we know that this delta V resistor for that one circuit, if it's a single loop, we know that the delta V resistor is negative IR. Then the delta V capacitor can say delta V capacitor, the potential difference is going to be negative Q, the charge on the capacitor, divided by the capacitance in farads. There we go. Now we are going to put the last thing, and that last thing is going to be capacitor charging and discharging. For charging, Q is equal to 1, small q is equal to bq, which is the maximum, multiplying 1 minus e to the negative t over tau, like that. Okay, then this is going to be for charging, for the charging of the capacitor. If you want to find the charge in it at any given time, then for the capacitor discharging, if you want to find the charge in it whilst it's discharging, it's going to be e to the negative t over tau. Okay, oh, so there we go. This is going to be for discharging. Remember, if they tell you that a capacitor is uncharged, then they say, what is the charge after 6 seconds? Of course it was charging, because at first it was uncharged. So after 6 seconds, we are still charging it. That's charging time. Then we can now start to talk about is discharging. Okay, now we should know that this tau is equal to RC, and we are done. These are all the formulas, and we are done, and we are now starting. So I'll be doing one question at a time, erasing, doing the next, erasing. So I've written all the formulas in one go to make it the way you're going to do it. Then we'll be just picking from here, and that's how easy the work is going to be. So now let's begin our work, which we have started in the next video. Goodbye for now.